All right, Mathletes, here's 3.3, properties of rational functions. So a rational function can be and will be defined as a ratio of two polynomials. The formula of a rational function takes the form of f of x is equal to p of x over q of x. So that's where this is a polynomial and this is a polynomial. Okay, and they can't be zero, because if you have zero in the numerator, then it's just a constant function of zero. If you have zero in the denominator, well, then we're dividing by zero. We don't want that either. Okay, so these are rational functions. So we're going to look at first the domain of rational functions. Well, the big thing with rational functions, the differences between them and polynomials, is that we're dividing by some sort of function. So I always got to remember we don't want to divide by zero. So like polynomials, it's for all real numbers. But you might have such that x cannot be equal to a value that would give you 0 in the denominator. Well, I know that 2 minus x, if x is equal to 2, it's going to be 0. On our graph, what it will look like is we get what we call a vertical asymptote, typically graphed with a dotted line. And that vertical asymptote is going to signify a spot where the graph does not exist. So the line in your graph isn't showing that that's a function, but what's really happening is in the programming of your calculator, as it's graphing over this way, it's getting closer and closer to that asymptote without ever crossing it, but at some point it's got to jump down and start graphing this one at the bottom. So that asymptote that's graphed there isn't actually a value at the function, but it's just the calculator processing going from positive infinity down to negative infinity. Okay, so for B, if I want to find factors and I have something that is a higher degree than a first degree, I might have to factor it so I can get their linear factors. Well, this one's nice because it's a difference of squares. I know that can be factored into x minus 4 and x plus 4. But realize on the top I still have x minus 4, that factor. So potentially in the graph those will cancel out, and we're not going to have an asymptote here at 4. But what we are going to have is we will still have a hole at 4. And the asymptote, because x minus 4 gives you a negative 4 as a 0 in the denominator, and that's not apparent on the numerator, that does appear as an asymptote in our graph. Okay, so as I state, the domain is for all real x's such that x is not equal to 4 and negative 4. So we have to include our holes and our asymptotes and to eliminate them from our domain. For C, we have that x is over x squared plus 9. Well, if we look at this, x squared plus 9, there isn't any real roots of that quadratic. Our roots of that quadratic are plus and minus 3i. We're not going to worry about complex numbers here. So for this one, if we cannot make that be 0, then it's for all real x's, and we don't have to do that. Notice that for many of the rational functions, they are what we call discontinuous, meaning we cannot draw the graph in its entirety without lifting up our pencil at some point. All right, so when we're graphing rational functions, first thing that's nice is to try and graph our vertical asymptotes. So my vertical asymptotes are when this is going to be 0. So I know that's going to be 0 when x is equal to negative 2. So at negative 2, I'm going to graph, typically with a dotted line, my asymptote. Okay? To know what's going to happen as we approach that asymptote, what we want to do is we want to graph some points to the left of it, and we want to graph some points to the right of it. So as I plug these in at negative 3, well, when I do 1 over negative 3 plus 2, I get negative 1 squared. Negative 1 squared is 1. So I get 1. So at negative 3, it's 1. Okay, at negative 4, well, negative 4 is going to be negative 2 squared, so I'm going to have 1 over 4. Negative 5, well, plus 2 is negative 3 squared is 9, so I get 1/9. So as I move further out here, it looks like I'm approaching 0 here, and it's increasing as I get to my asymptote here. So I'm going to have a graph that looks something like this. So it gets infinitely close to that asymptote, but it never touches it. So on the other side of it, here at negative 1 and 0 and 1, I want to know what's happening. Well, when I plug in negative 1 into this, I get 1 squared. So again, I'm at 1. That's positive. Okay, and at 0, I get 4, so I'm going to be 1/4. And it's going to be 3. 3 squared is 1/9. So remember, this is typical of an even function or even degree here at our asymptote. Because this multiplicity is even, I'm going to have even type symmetry where it's going to have reflection symmetry that can reflect across its asymptote. So here, I'm going to have a graph that comes down. Again, never going to have something negative here, because I should see that because I'm squaring everything, it's always positive up there. Well, the numerator is 1, so that's always positive. So you can see all my graph there is above our x-axis. Let's look at another one. So f of x equals negative 1, x squared minus 4x minus 5. Well, to find my asymptotes, and where this is equal to 0, again, finding a 0 of a quadratic, I would want a factor. So I can do x minus 5 and x plus 1. These are going to give rise to zeros at x equals 5 and negative 1, which in turn are asymptotes. So as I plot my asymptotes at x equals 5, so 2, 4, 5, so asymptote is here at x equals 5, and another one at negative 1. So I have my asymptotes there. So again, I want to make a table to find points to the left and to the right of the asymptotes to see what's happening next to them. Okay, so as I plug in negative 2, I'm going to have 1 over, negative 1 over, negative 2 minus 5 is going to be negative 7. Negative 2 plus 1 is negative 1, so then I'm going to be negative 1. So I'm going to be negative 1/7. Okay, at negative 3, well, negative 3, I'm going to get negative 1 over negative 8, and negative 3 plus 1 is negative 2, so I'm going to be negative 1/16, and at negative 4, I'm going to be negative 9 times negative 4 plus 1 is negative 3, so I get negative 1 over 27. So getting smaller and smaller as I move out. At negative 2, I'm negative 1/7, so I'm somewhere around there. And as I'm at negative 3, I get smaller and smaller. And so as I'm graphing this, it's never going to be positive because I always have this here being positive. So I am going to keep this, and I get infinitely close to the asymptote with never crossing it. So what's happening in between my asymptotes? So when I plug in 0, I'm going to get negative 1 over negative 5 times 1. So I get 1/5. Okay, at 1, I'm going to get negative 1 over negative 4, and times 2. So I'm going to get 1/8. Okay, at 2, I'm going to get negative 1 over negative 3 times 3 is equal to 1/9. And then at 4, I'm going to be negative 1 over negative 1 times 4 plus 1 is 5. So I'm back to 1/5. Okay, so at 0, I have a value of 1/5. At 1, I'm 1/8, 1/9, even smaller. Then it kind of goes up, and it goes up there. So what I'm going to do is, as they get up and closer to the asymptote, it's going to go to infinity. And this one's going to go up to infinity as well. And I have that shape graph there. So what happens to the right of my asymptote? So then I'm going to get 6, so negative 1. 6 minus 5 is going to be 1. And 6 plus 1 is 7. So I get negative 1/7. At 7, I'm going to get negative 1 over 2. And 7 plus 1 is 8. So I'm going to get negative 1/16. And 8 is going to be negative 1, 3. And 8 plus 1 is 9. So I'm going to get negative 1/27. So as I go and move away on my x-axis, I'm getting smaller and smaller negatively. So negative 1/7, and smaller and smaller and smaller and closer to that 0, never really approaching, but as I got closer to my asymptote, I got bigger negatively, so I'm going to get larger as I get closer to that asymptote from the right. Okay, so that's that graph. Okay, some horizontal asymptotes. So we know vertical asymptotes is what makes our denominator 0. Well, horizontal asymptotes, we have 3 different cases. One, it's when the numerator's degree is less than the denominator. Okay, then that horizontal asymptote is 0. So x to the first is smaller degree than x to the second. Notice all the ones we did previously, these were of that case, and that's why we had a horizontal asymptote at 0. So that won't always be the case. The second case we'll see is when the degree in the numerator is equal to the degree in the denominator. Degree 2, degree 2. Well then, what we do is just take our coefficients in front of our highest power, and that will be our horizontal asymptote. So our horizontal asymptote there is when y is equal to 2/3. Okay, it's taking the limit. As those values get really, really large, or really, really small, those 2/3 are going to remain constant throughout. Okay, and our third case, a case we'll look at and explore in the following lesson, is the oblique asymptote, when our numerator has a higher degree than a denominator. Then we're going to have asymptotes that potentially are of the form of a line, and we can even get some crazy ones where our asymptotes are of other polynomials. So we could have an asymptote that's actually a parabola. So let's look at an example of these. Okay, so here I can see that 3 over x squared minus 4. This is when the denominator has a higher degree. So that means our horizontal asymptote is right here at y equals 0. Well, I want to find my x asymptotes too. So that's going to be factored to the denominator, and I get x minus 2 times x plus 2 over 3. Well, that's going to give rise to 1 at 2 and 1 at negative 2. So as I want to make a table here and figure out what's happening at these graphs, I'm going to think at -3, -4, -5, what's happening as it approaches -2. Well, if I put -3 in there, I'm going to have 3 over -5 times -1, which is equal to 3 over 5. Okay, -4, so that's going to be 3 over -6. -4 times that is going to be -2. So this is going to be 3 over 12, or 1/4. So we're getting smaller. And I should start recognizing a pattern that, all right, I'm going to remain being positive, and this value is going to get smaller and smaller. I can do it one more test here, and I get -7 and a -3. So I get 3 over 21, which is 1/7. So as I graph these, -3 and 3/5. Okay, as I get out, I'm getting smaller, smaller, smaller. Gonna get closer and closer to that asymptote, but never being less than 0. And as I get closer to -2 from the left, it's going to get positive. Okay, so let's look at a table for the middle values. So I'm going to look at the values from -1, 0, and 1. So I put 3 in. -1 times -2 is -3. -1 plus 2 is going to be 1. And I get -1 there. When I plug in 0, I get 3 over -2 times a +2. And I get 3 over 4, and that's negative, and 1 is going to be 3 over, when I plug in 1, I get 1 minus 2, and that's going to be -1, times 1 plus 2 is 3, and I get a -1 again. So at these values, I'm at -1, 3/4, -1, so I'm going to have this U-shaped graph. It gets very close to my asymptotes and go on forever like that. Notice x minus 2, it's a multiplicity of 1. It's odd. So the symmetry around that asymptote is odd. That it's somewhat rotated there. Okay. Now for the values to the right of our asymptote at 2, I have plug in 3. So I'm going to get 3 over 3 minus 2 is going to be 1 times 3 plus 2, which is 5. So I'm going to get 3/5. And then I'm going to get 3 over 2 times 6, which is going to be 3 over 12, which is 1/4. Okay, and then at 5, I'm going to have 3 over 3 over 7, which is equal to 1/7. So as I can see that these are positive as well. So at 3, I'm 3/5. As I get closer, smaller and smaller as we go out to positive infinity. As I reach my asymptote, they start increasing. All right, so there is my graph there. Let's look at one more example here. So find the vertical and horizontal asymptote. So notice my degrees here are 1 and 1. So then I look at my coefficients, imaginary 1 there, and I see that my coefficients are equal to 2 over 1 in front of my highest degree terms. So my horizontal asymptote is at x equals 2. sorry, y equals 2. Okay, and then for here, I'm going to get my vertical asymptotes when that's equal to 0. Well, that's at 3. So at 1, 2, 3. Okay, that multiplicity of that denominator 0 appears to be 1, so I'm expecting some odd type of symmetry with respect to that asymptote at 3, not necessarily our horizontal symmetry, but our point symmetry there. Okay, so again, I have my asymptotes. Let's look at things happening to the left and right. So when x is 2, 1, 0. So when it is 2, I get 5 up top over negative 1. When it is 1, I get 2 plus 1 is 3 over negative 2. When it's 0, I get 1 over negative 3. So as I plot these points, this being my x and that being my y, I can see at x being 2, I'm at negative 5. At x being 1, I'm negative 3/2, so negative 1.5. Okay. At 0, I'm negative 1/3. So this negative 1.5, and then negative 1/3. Okay, and as I get further out, okay, I can test another point at negative 1. I can see that I'm going to be negative 2 plus 1 is going to be negative 1 up top, and I'm going to be negative 4. So now I'm at 1/4. You can see I'm going to start going above the axis, but never going above the 2. So I have an asymptote or a graph that looks like that. And now to test the points to the right of my asymptote, so at 4, 5, 6, 7, get x and y. At x equals 4, I get 9 over 1. At 5, I get 11 over 2. At 6, I get 13 over 3. At 7, I get 15 over 4. So as I graph these, at 4, I'm at 9. Okay. At 5, I'm at 11 over 2, which is 5.5. So I have that point. At 6, I'm about 4 1/3. At 7, I'm at 3 3/4. And I can see as I'm going to get further and further out, I'm going to get closer and closer to that 2. Okay, you can imagine if this is a very large number, let's just say if x was 1,000, okay, it should be very, very close to 2, and we can see that in our equation because we get 2,001 over 997. Well, this is very close to 2. Okay, and as we get further and further out, that -3 and that +1 is not going to pay that much significance because these numbers are so large as we go to infinity that it's going to be very close to 2 and get closer and closer to as we go out. All right, make sure you highlight questions you have and bring them to class tomorrow.